Patricia Delafuente is part of the adjunct graduate data science faculty with the University of Maryland, Baltimore County, and the senior director of data science for New Wave Telecom and Technologies. She is a data scientist with over 20 years of database engineering, business intelligence, and analytics experience. She is a university ambassador for NVIDIA and is certified to teach several NVIDIA Deep Learning Institute courses. Her interests are machine learning, text mining, and using GPUs and distributed database processing to improve the performance of analyzing and processing big data. Patty will cover the critical information and points to enable your innovation and infrastructure for AI, as well as some of the tools you will need. Is your company ready for AI? Patty, you have the stage.
Thank you, Eric. Thank you, Cloud Summit team. I feel very honored to be here. Talking about technology is one of my favorite things to do. Why am I talking to you about enabling IT infrastructure for AI and not diving into some of the cool AI tools and showing you some cool robotics and stuff that we could do? Because there's something that you need to do before you can jump into AI. You really need to make sure you're ready for it, that you have the right infrastructure that can support it. I won't go into my bio. Let's just take my word for it that I'm super geek. I love AI. I have been in the industry for over 22 years. I've had lots of hands-on experience with data migrations, with database engineering, even before worked with hosting big data, even before it was called big data. And then I jumped into the data lake along with everybody else and began to specialize in the AI arena, and went back to school, got another master's degree in analytics so I could up my math game. But I'd like to share with you some of the personal experiences I've had with some of the lessons I've learned with getting other companies ready, and companies that I personally worked for, helping them get their data infrastructure ready for AI, and shoring up some of their weaknesses, helping you with a checklist that you might need. Many organizations are interested in leveraging analytics. How can they do business better? How can they target their audience? How can they tell stories with their data? How can they improve healthcare outcomes? There's all sorts of amazing things that you can do with AI. But before you do that, you need to make sure you're ready for it. And so we're going to talk about some of the barriers. You're going to deal with more than just your technology and your infrastructure. You're going to deal with culture. There's going to be a whole lot of things you're going to have to consider. What is AI? Well, how do you define AI? We'll talk about how I define AI and see if we can get to some sort of a common ground. Technology innovation, we'll talk about that. We'll talk about data. We're going to talk about data separately than just the infrastructure, because there's some things that you need to consider with the data that you have. Data sharing, and then we'll talk about some data analytics tools. We have a whole lot of things to talk about. I won't have a lot of time to deep dive into some of the specifics, but that's something we could do in the future, and you can always ask me questions in the future. So some of the barriers to AI. One of the things that hit home with me, even you think you get an idea for a new project or effort, or you see that a way that AI can solve a problem within your business, and you pitch an idea and you know it will work, but then you run into issues and you can't get it off the ground. So one of the things that I encountered personally is something called functional fixedness. And this is a it was a term that was we first heard of with somebody named Carl Dunker. Back in 1945, he identified this cognitive bias that folks had. It was a mental block that some folks could not look at an object. If they knew of a purpose of an object, they couldn't use it in a new way to solve a problem. And the example that he did was he actually had a study where he had folks, he gave them a matchbox and a candle, and so he gave them a match, a candle, and a tack box, a box that held a bunch of taxes, and there were a bunch of taxes in it. And he wanted you to take the candle and affix it to a wall and light it. And he found that adults had a lot of problems solving this problem, but kids could actually solve it. And of course, you may have already figured it out, but the solution was to empty the tack box out, put the candle in the tack box, use its thumbtack to tack it to the wall, and then light it. But so many folks could not get past the concept that the tack box was meant to hold thumbtacks. And then another example, and I had a friend of mine gave me this riddle not too long ago, and I didn't get it right the first time. I actually cheated. But he gave me a scenario of, okay, so you walk into a room and Romeo and Juliet, they're both dead on the floor and there's water and glass, and a window's open. What happened? And I'm like, well, were they poisoned? Did she, was there a knife around, or was a glass sharp like a knife? Did she stab herself after Rome, or I had all these, I was going along with the play. Well, the answer was that Romeo and Juliet are actually fish, and they were in a fishbowl, and the fishbowl knocked over, and so I instantly leaped to the fact that of the play because of the name. So the lesson here is to question everything, and not just, and think outside the box. So, and both examples. And you can probably, if you think back, if you look at the even America's historical evolution in terms of technology, transportation, stuff like that, you've seen that everybody had to go through, Ford had to go through, folks wanting to continue to use horses for transportation and stuff. So his famous saying was, if people had asked me if I had asked what people wanted, they would have told me they wanted a new horse instead of a car. So change is something that we all have to struggle with. And another example, and then some of the other things that you will encounter, especially in the government, is culture and risk aversion. So risk aversion, you can kind of understand. So if you work for a company, or if you're doing business with a company that has lots of, that has an important mission to do, like paying disability claims, health insurance, processing taxes, and these, or even a bank, and you have these mainframe applications that are doing work and with billions of transactions a day. They don't want anything to break or interfere with that. It's working, so there's a reluctance to try something new that might break that. The other thing is the culture too. In private industry, you might have another mindset where they have an existing client base and they don't want to lose revenue from that existing client base. So an example that I have from that, this is something that I talk about with many of my students, is back in the 60s, 70s, one of the things that a lot of the industries were trying to do was figure a way to improve data storage. So it was really tracking, like, even Social Security numbers and retirement and IRS records on all of the the NASA, like all of the space records, trying to track that on millions of paper, a bunch of paper was really, was not the best idea. So they were trying to look at ways to store it, to use computing technology to store it. And some of the earlier database systems were file-based, and they were very limited. You had sort of these big, huge files that you would just try to crunch it through the files. It was very sequential based, first in and first out. And there was a lot of limits to that, where it was tightly coupled to the application. So if you had to add a new field, you had to do it in all those different areas and all your different lines of codes and your application codes, or you would break the whole system. So it was very limited. And also, if you had a file that was used that stored employee records here, and then there was a related record, maybe health insurance record or something over here, you couldn't naturally relate those two files together. So you had to go through a lot of process. You had all of these batch jobs that would run at night, and it was just very time consuming. So one of the earlier database models there were some earlier things called network object model and hierarchical model, which still had limitations, but they were a little bit better at doing some relationship tracking between records. But even those were extremely limited. So you had IBM employed somebody named E.F. Codd, and he had wrote this seminal paper called The Relational Model of Data for Large Shared Data Banks. It's required reading for my students. But what he pretty much came up with the theory behind relational databases. And the paper's brilliant if you get a chance to read it. Again, it's called The Relational Model of Data for Large Shared Data Banks, and it's by E.F. Codd. He really solved the problem of storing data and eliminating the data anomalies and having true data consistency and being able to update records and stuff like that. So I don't even know that if he knew how brilliant that paper was, but at the time, IBM did not run to market with a product based on that, because they didn't want to cannibalize their existing customers that were using their current systems of their hierarchical models and their network models. So so they didn't let them go to market, but he had a great manager. They let him continue to work on it. He wrote a book, and then he also developed the SQL language, the SQL query language that we know today. And but they still didn't market it and develop a product. So there was a different company who got hold of that paper, and then they thought it was brilliant, and they developed a product. They were first to market with it, and they garnered the market share. And then you found IBM later on came up with their own version, but that company that was first to market was called Oracle. So, and I'm sure you've all heard of that. So that's an example of what can happen with where you can easily get behind the times by being too risk adverse and not keeping an eye on the future. So having a vision of what you want to do and where you want to go is important, and keeping an eye on technology. And you're going to have some determine what your level of risk is. And you can mitigate risk, but you are going to have to take on some risk and not be afraid of failure in a safe way. And if you don't take that risk of failure, you're really not going to be able to move forward the way that you want to, and depending on the company. The other barrier is limited skills in new platforms. So definitely helps to reduce your risk and to convince your culture if you can show a proof of concept that can show it working. If you can acquire skills in the new platform, if you don't have those skills, or if you don't have a team that has the capacity or the aptitude to learn, because you have different skill sets. Some people are really good at being detail oriented and keeping things running, but they may not be forward thinking. So it takes a good mix. If you don't have folks who really can jump in and figure out new technology and how it can apply and work with your subject matter experts, you may need to look outside your company and hire a company that is skilled in that new platform that can show you, come in and do a proof of concept. And then the other barriers, which I see, I've seen pretty recently, and everybody sees every day, is your complex legacy systems. It's coupled with the risk aversion and trying to keep the lights on. That in itself is a challenge. And that's another topic. So, but anyway, so let's talk about AI. What is AI? So I define AI, and I think Wiki defines it pretty much the same way. Artificial intelligence is a way to use machines to improve or emulate human or biological performance. And I usually they say human, but I also say biological because I've seen machines used to emulate more than just humans. So I think at the Johns Hopkins Applied Physics Lab, they had this really cool robotic worm. And so they used they were emulating the neural network model of a human brain, but they started off with a worm because they only have 256 neural pathways. A human brain has 87 billion. So they started off small, but it was pretty cool because I observed it. It did act like a worm. It was trying to look for sources of sunlight and food. It was interesting. So okay, but enough of that. So AI is a pretty broad category though, and it has lots of subcategories, and the subcategories can include things like robotics, machine learning, natural language processing, computer vision, robotic process automation. So a lot of times, and machine learning is kind of what is going to be more of the focus of this talk. And so machine learning is really a way of using data, past historical data, and having computers being able to train and build models based on that data and make inferences on incoming data. It's dependent on both data and analytic algorithms. And then if you target it to the business questions that really are foundational to helping your business grow, it really is a way to inform company and organizational decision making. For retail companies, it can be used to target the right mix of products and marketing. For healthcare companies, especially for hospitals and stuff, leveraging analytics can help improve your healthcare outcomes by learning, what treatments work and what don't work, and prescribe and getting prescriptive almost to help physicians and people. It's more of a tool to help with your decision making. I don't see it as a way to replace it. I just see it as in certain companies to help augment that. So it's technical innovation, and so that what's really driving where we are today is computing power, data availability, and optimized analytics. So computing power, we have things that we just didn't have before. Besides the CPU and optimization, GPUs, graphics processing units, have really gone. The use of that has really enabled a way to process things like computer images and natural language processing, things that can be chunked down in a low power way. It's really enabled robotics to do things it couldn't do before. I'm a big fan of graphics processing units and robotics. And this is an example. This has a GPU on it. It's got 256 CUDA cores. And it's really enabled a way in a small form factor to, it has a little camera. So GPUs can process complex operations in a low power format and just do things like, it's really the core technology behind things like self-driving cars. And then the data itself, all of the computer images and stuff. So data availability is the other innovation that's happened. We have so much data. And back in the 90s, I remember playing around with some speech recognition tools, and even at most, you would get, like, even after hours and hours of training it to recognize my voice, I would get like 60–70% accuracy. Well, combining that with the advances in computing power, and then the other piece was optimize the optimized analytics. There's been a lot of improvements with the way neural networks operate, and combining their capability with computing power, and it's just really enabled you to get to higher than 90% accuracy and do things that you haven't been able to do before. Some of the advances in computer vision are just insanely crazy compared to how they used to be. I think like ImageNet, there was an ImageNet competition, and once they optimized the network infrastructure behind the neural networks, and AlexNet was the first group that was the first model that was optimized by a group of guys, and one of them was named Alex. I don't remember all their names off the top of my head, but they figured out a way to optimize a neural network, and they just won that competition hands down. And once they showed everybody else how to do that, then the accuracy improved to the point that they were able to stop the competition. And so it's an exciting time, and there's so much potential for AI. It's still evolving. So let's talk about data. So data is worth a mention because one of the things that I found, and I've seen people learn the hard way, is doesn't matter if you have a wonderful team of analytic staff, if you have the most amazing machine learning software and computing power, you will still have problems if you don't have the data that you need to build and train your analytic models. Why is this important? Why am I talking about data and not just everything else around it? Well, in order to build a machine learning model, in order to make predictions, you need to have the right data. So typically you start with historical data. You have a data set, you shape it, you have to have some sort of structure to it. And in particular with your, natural language processing and computer vision is a little bit different. But for other things like being able to predict whether advertising dollars affect the amount of sales, whether they go up or down, to figure out something like what affects the amount of people who will attend a concert, or what is somebody's batting average, what was the effect of that depending on the player's attributes for baseball. Before you can predict any of that, you have to have data, and it has to be in a format. You have to take that existing historical data, have it shaped into essentially a set of columns and rows. And the columns need to be meaningful. So you have to have the right data itself you have to have the right columns. So each of these columns, one of the columns will be something that you're trying to predict, and then the other columns are going to be the things that affect that target that you're trying to predict. And if you don't have the right variables, if you don't have the right columns that define, that have an effect on that, you might not have the right data. Then your model isn't going to be as effective. And so, and I say that because I've personally experienced it in the past. Here I'm listing an example of like if you wanted to see if smoking resulted in vision problems. So if you had a column or better known as a feature that it was in your database, what if you tracked whether they were blind but not if they smoked? So how would you ever be able to predict if smoking affected vision problems if you've never tracked how they smoked? Some of the real world examples that I personally encountered was I in the past did a study on disability fraud, and but I couldn't get access to and confirm which of the claims were actually confirmed to be fraudulent. At best I could do was figure out which ones were flagged. And so that really decreases the ability of what I was actually able to predict. So and then other examples, and I'm thinking of something that I actually worked on, but I am not at liberty to talk about that particular use case, but also I'll give you a similar example. Let's just say I worked in a university and I was giving financial aid, but I only could give financial aid if you didn't have financial resources above a certain level. So, and in order, and I wanted to know if I needed to know if I figured out, like if I decided that somebody wasn't entitled to financial aid or if they received an overpayment, I wanted to figure out if it was because of, do a study that was because of financial, because of they had too much of financial resources. But I also wanted to see if perhaps, I decided to pay for data exchange with financial institutions so that I could get financial records, and then I could use that to see if they had financial resources. But so what if I wanted to figure out whether that was useful or not, if whether there was a return on investment for paying these financial institutions to get their records? And I wanted to see if it actually resulted in me identifying like whether people were being overpaid because of they had too many financial resources. But if I had never actually tracked the reason that I noticed that they were overpaid, so if I never actually stored the reason and I just said this person's overpaid, then and later on I try to do a study on that, I wouldn't be able to really identify whether I could identify whether somebody was overpaid, but I wouldn't be able to figure out why if I never tracked that reason. So I say this because this is very important as you're implementing new data projects, even whether it's a project to identify overpayments, fraud, claims records, healthcare records. So you really need to start asking business questions as you go. Like, what kind of business questions am I going to answer down the road that I might need, that I may need to measure something. Make sure you have a clear understanding of what kind of important business questions, reports you're going to have to do, so that you can make sure that you're tracking the data up front. If you think about the business process of what a worker has to do, some of the decisions they have to make when they're processing a piece of work, are those decisions that they're making, are those tracked anywhere? Because if you need to understand that decision-making piece and track any of those things, or even be able to predict or automate some of those decisions, then you have to track the data around that. I hope that sinks in, because if you're not asking the right business questions and you're not storing the right data, you're not going to be able to automate a lot of those things. It's just going to be in somebody's head. Okay, so now we're going to move on to infrastructure planning. And so the most important thing that you really need to talk about in terms of an infrastructure planning for AI is your business needs. Business really does drive your infrastructure. It really isn't always a better idea to build it and they will come. You really need to make sure, especially if you're a federal agency or you really need to figure out what are your outcomes. Especially with regards to AI projects, be specific. So if you're a bank and you want to enable a way to identify a customer as a high risk for not paying back a loan, then that's the business use case. If you happen to be a payroll department and you want to figure out if is it that you want to figure out if implementing an electronic policy system reduces payroll calculation errors. If you are, like, if you think in terms of the federal agencies, they have all these big policy manuals, and if you, would AI help you, if you could integrate policy within the decision-making process of those applications, would being able to give them access to policy quicker, would that reduce errors made during those applications? Those could be some of the things that you could measure. Understanding those kind of business questions will help you target your use cases, figure out what kind of data you need. And I talk a little bit about data because there's a big, and data use cases, because there's a big difference between transactional systems and business intelligence systems. And it's important for you to know the difference and not try to use the same database for everything. In the old days, you only had relational databases. You had your flat file databases and you had relational databases. And then we had to do special things with relational databases to improve the performance for our reporting applications. So, but big data has changed all that. So you still need your relational databases, but you don't necessarily, but you have better ways of doing your management information and your analytic reports and getting your analytic needs being taken care of. So, but back to the business needs. Make sure you understand your use cases. And as I just said, target your appropriate SQL engines, your data engines, and your storage. What data do you need? Is the right data being captured? Is the data available? Do you have access to the data? All of that especially if you're a federal agency, can be challenging, because what if you have all of this data but nobody can access it? The data scientists can't access it. I personally encountered that when I worked for Social Security. When I was doing one study, first the ethics department told me I couldn't do the study. And so I thought, well, okay, I'm going to have to do something different. But then I worked through the red tape, and instead of just giving up, I realized that I just wasn't answering. Like, I needed to navigate the red tape a little bit better and network with my colleagues to make sure that all of the questions that the ethics department had were answered, and that they knew that we were doing the study for a good reason, and it wasn't for personal gain. And that we were controlling that the security and integrity was maintained. So I had to address the governance issue and the access and the audit and go through the proper channels. And then I was able to do it. So you can do those things, but they just may take you a little bit longer. So that establish your data governance, access, and audit plans. You're going to have to know that up front, like how, you don't want data access to be a roadblock to your AI needs. What you want to do is plan for the red tape and make sure you have processes in place that they can get access to the data and the systems in a safe and secure way. And just be patient and persistent and transparent. Assess your existing hardware and software infrastructure. Absolutely, that is one of the most important things, and I'll talk more about that in the next slide. Ensure that the required data is captured. I've said that. Hopefully that's starting to sink in now. You might already think of examples of where you've personally encountered that issue. Plan for your data storage and compute layer strategies. We'll talk more about that too. It's kind of related to step one, where you assess your hardware and software infrastructure. You can't really you may make mistakes and your new technology investments if you aren't aware of all of the existing investments you already have. And then invest in modern analytic tools for model building. Yes, we'll talk more about that later. But yes, you need to look at your existing infrastructure. You need to have your policy and processes in place. You need to efficiently plan for moving forward with data storage and computing layers, things, cloud computing, figure out cloud computing versus on-premise, and do it in a smart way that capitalizes on your existing investments. And then make sure that when you do all this, that you have the right tools so that your data scientists can actually work with this data and be productive and make it and help you leverage your investments and actually get to the end results of what the whole point you're in moving towards AI is to make use of it and help you perform better. So you need to make sure that they have the tools to get there and that they have the efficient tools. And then plan for the mix of the skill sets and staff that you need. Know your current state before you plan alternatives. Absolutely. So existing software investments, costs, and implementations. How many databases do you have? What platforms are they on? Moving from on-premise to the cloud, if that's your goal, you really need to really, before you decide where you're going to put it in the cloud, and understand your use cases. Do you have OLAP services? So, and I say that because back in the day with relational databases, so relational databases are perfect at what they need to do, and that's to maintain your data consistency and process transactions as fast as they can, row-level transactions, handle lots of incoming transactions efficiently. But they weren't great at reporting applications. And so the reporting applications with all of the joins that you would have to do were very slow. And then also your traditional relational database systems. And I'll just map this out for you real quick. If you had a, hopefully you guys could see this. If you had a traditional, database system, you could only scale up. So you might have like a storage area network. So, and then you would have your data stored on here. You could almost treat this like an internal drive, because usually you would have fiber channel connectivity between the two. But you could only scale up. That means you could increase your CPU and your RAM, and then you would also optimize your indexes. And so your goal was to improve write performance. But when it came to report, and you would normalize your data and have lots of tables, but when you needed to do reports, it was very, your reports would just take forever to run. So some of the things that we used to do is we used to take the data and move it to a data warehouse. And so we would structure the data in a different way. We would have snapshots, and we would have a star schema, and then we would do things like we would build dimensions and measures, and we would cube them. And we would process, these were called OLAP cubes, and OLAP stands for Online Analytic Processing. And we would process these cubes at night, and then we would hook reports up to these cubes, and that would help your business intelligence reports. But again, you could only scale up, you couldn't scale out. And so where big data has changed this is especially with Hadoop, what would happen is you would have, and this was expensive hardware too, by the way. These servers were not cheap. I remember back in back in the early 2000s, budgeting $100,000 for a terabyte of data, and then when the prices went down, budgeting like $40,000 for a terabyte of data. So with your big data, what you then had was lots of you could add like 100 low-cost servers and stuff them full of hard drives, and then you would have like your master node, and you would have your data nodes. And then you could actually take data, and you could take your data and stream it across all your data nodes. And then you could also take your computing operations, your queries, and your Java procedures, MapReduce jobs, and you could also scale out across the different data nodes. And so you could truly do things cheap. I know at one company that I worked for, we had a Hadoop cluster, and then a terabyte of storage was only like $60 every 5 years, and it was dirt cheap. So, and now you have the cloud on top of all this. So, and then we'll talk more about the cloud in a little bit, but the cloud doesn't change this. All it changes is you don't manage this anymore, but the cloud still has the same limitations and optimizations that you would have on premise. If you're going to scale out, you're going to have it in a big data system. If you're going to have a relational database, you're still going to have these kind of limitations. So you can still only scale up in a relational database system like SQL Server or Oracle, but you would want to still use that for a relational database. But if you have a big data analytic database, you would want to go towards a NoSQL or column store sort of distributed database system. And so if you can scale out on premise, you can scale out in the cloud. So I say that because a lot of people might have a misconception that if I'm moving a SQL Server instance to the cloud, that I can suddenly scale out. That's not true. You're still limited to scaling up. So anyways, okay, so I diverged a little bit, but I wanted to kind of hit home on you should understand your use cases. And then the other thing about distributed databases is because they are stored differently, your data is stored in a column-oriented way that helps you retrieve reports and do your aggregates and stuff more efficiently than a relational database. You don't necessarily need to go through the hassle of building your dimensions and cubes, your dimensions and measures in cubes. You don't have to do that anymore. You don't have to do all these transformations. You can actually just create a data lake. That's, and then you go right into your reports, because you now have computing power that you didn't before, and you're not worried about the performance issues you had previously. So, so lots of your new big data solutions don't have the OLAP capabilities anymore. You can still get the end results, but you're just going to do it a little bit differently. So your OLAP services aren't going to map cleanly to big data type features, but it's still probably worth the efforts to migrate, because you can do it. You can scale out. You can take advantages of your big data technology. And it'll be hardware-wise, it'll be more efficient and in the long run. Other things you have to consider: size of your data. Obviously, if you have a small database, going to a distributed database system actually could slow things down if your data is super small, because there's some overhead with getting to this distributed format. It actually could increase your latency if you have a really small database that performs pretty fast as it is on premise. The cost of your software licenses, data, and storage. So if you have the mainframe, you need to look at and you're moving to the cloud, you need to look at all of that. You need to look at your existing investments, in other words, and map that out and have a planned strategy and really get a good accounting of all that. Your hardware and software contracts. So, I mean, there's a big difference between being a startup that has no data centers, no engineering staff, no contract support agreements, no between somebody like one of your large federal agencies who may have several data centers. They have an existing infrastructure of systems engineers, network engineers, security engineers. They may have cloud contract agreements. Among other things, but they also may have existing server BPAs and stuff like that. There was an example was recently, and you might have budget limitations too. So the cloud is not cheap. Neither is the on-premise stuff. I mean, if you're a new startup and you're trying, you may not want to build a new data center. You might not want to invest in all this stuff. You might want to budget a couple $100,000 a year to go to the cloud, and then makes sense. But if you're an existing mature company with this big data center and you don't plan on reducing your footprint, the cloud's going to be an extra expense. So you need to look at both things. The cloud, there's things in the cloud you'll want to do, but you also still want to capitalize on your existing on-premise investments. Okay, so I have this slide in here just to get back to the data part. I already kind of diagrammed out, like I talked about relational databases and then the big data databases. So be very careful with trying to take all of if you have an existing application that is, and I know this is a talk on AI, but I just want you to be careful. This is why I'm telling you to understand your use case. If you have an application that is you really need maximum data integrity, and you need to define the relationships between the two. If you have a financial system, a ledger type of system, a human resources system, and it's in a database, a relational database, you want the record keeping part where you're tracking each individual record, and you need that to be consistent. I do not recommend that you put that in a big data type of solution. What you should be putting in is the pieces from that, snapshots of that to report off of and do AI from. Don't move everything over, move the pieces over that make sense. So be careful with just jumping into the whole big data lake and not really understanding which pieces of your application should be in that data lake. You may have vendors that will try to sell you that it'll solve everything. It's not true. So be very careful. Big data is wonderful. There's a lot of amazing things that it can do. Just do it. Make sure you understand your use case. They may tell you that they're ACID compliant, and ACID is the term that we use for transaction integrity. So and that means, like, that's not the goal of this conversation, so I'm not going to get into this too deep. But it's just the piece where we measure that each transaction succeeds or fails, that our data is consistent, that one transaction that has an issue doesn't affect another transaction, and that the transactions persist. So there are some big data solutions that have some transactional capability, and they do have some ACID compliance, but they're still geared for data warehouses. They're not geared to replace relational databases or records-based system. So if you find that you have like a high volume transactional based system where it's important that every transaction is written as fast as possible to disk with a super low latency, then that should definitely still remain in a relational database. If you're worried about costs, there's open source versions. You can go to MySQL or something like that. You can do MySQL in the cloud. So just be aware of the differences between transactional and distributed databases. And then the other piece of that with regards to distributed databases is the CAP theorem. So, and the CAP theorem states that that at most for a distributed system, that you can only solve two of these things. You can only be consistent or available, but you can't be all three. You can't have true consistency and availability and partition tolerance. And I don't have time to go deep into that. But what I'll say is that that what you have with some of these systems is what they're able to do is give you eventual consistency. So if there's lots of data nodes, then depending on what node you hit, you might not see a change in a record until later on once everything's replicated. So be aware of that. And when you're talking about big data, when you're talking about like Google, who's indexing all of the world's websites, that's fine for them. It's fine for them to not have everything synchronized away. Eventually, it will be, but it's not fine if you have some critical stock market change or a record change. You know, if I'm let's just say that I have an account where I need to access a critical monitoring system, but I had a change to my record and I can only get in part of the time because not all of the nodes have replicated. Well, that's bad. I need to get in at any time that I want to. So just be aware of that. Make sure, and I know that you're not going to remember all of these things. I'm just hoping that you'll at least ask the questions and question everything. That's my goal, is to question it enough so that you know that the pieces of your application, that you're putting them in the right spot. And there's lots of different database systems. And so, so you have your relational database systems, you have your distributed NoSQL database systems. NewSQL is kind of a new breed where they're trying to really add a lot of your transactional capability to some of your column store, your big data databases. They've made lots of headway. Just be very careful. Make sure you test it. Make sure you test the latency. Just don't dive right in. And then blockchain. Blockchain and mainframe are very similar, and just be aware that, like blockchain is a ledger-based system, doesn't solve everything. A blockchain is great in that, it has a different use case than your other databases. It's sequential with the same kind of use case that your relational database systems have. It's also more similar to your older flat file systems. Now, what's different about it is just the actual where the use case for it was for authentication and transparency. But the authentication was that so you didn't have a single point of authentication, and so you didn't have a single point of control. It was peer based, and so that's where it differs from relational database systems. But at the same time, in order for it to work, all of the peers have to have a copy of the entire database, and the transaction is completed in its entirety across one peer. It's not truly distributed across the different nodes. So I warn you about that, because until, I know they're working on making it, improving the performance and stuff. But if you jump right into blockchain for big data, it's not going to distribute and perform like a big data, like a NoSQL database would, because you can't actually chunk you can't actually store the data across a distributed group of servers, and you cannot actually divide the transaction across a distributed group of servers like you can with your big data databases. Because again, with the CAP theorem, you can't have all three. And so for a blockchain to be consistent, it has to complete and store all of its data at one point, and then it replicates that across. And I mean, that's a simplified way of doing it. I'm just warning you, be careful of the use case and question everything. Okay. And then this is just a slide just to talk, again, this slide's a little bit older. This is from Gartner, where I just highlighting the different use cases. You have your streaming, your batch processes. Your batch processes means you have a bunch of jobs that work at night, and that's when you can do your bulk imports, your data transformations. Ad hoc, that's more of your analytic type of workloads where we're doing AI and building models and maybe exploring data. Operational, that's where you get into your transactional based systems, and then your streaming, where you might be streaming in videos or sensor readings from security checkpoints and stuff like that. So they're all use cases, and my point with the slide is for you to figure out what is your use case for the application you're using, and then you can start to target your right products. Okay, so moving on, because I'm getting short on time, which is not unusual for me. So cloud data sharing, I want to give an honorable mention to the Snowflake Data Warehouse, because they're one of I've worked with this product quite a bit, and one of the things that they're able to do that I haven't seen done from a lot of the other databases is you can actually store, this is a data warehouse that is cloud native, meaning it's never been on premise, it's built for the cloud. It is a data warehouse, so it's not a transactional based system, but what it can do is you can enable access to other cloud accounts, so as long as they're in the same region. So let's just say that that Eric from the Cloud Data Summit had an Azure account in the same region, and I had an Azure account, and I could granularly give him access to a certain row of data that I know he needs to look at, and he can connect to my data in a secure way, and just the data that I want him to see. I don't have to pay for enabling him to creating that share and giving him access. It doesn't cost me anything. All I got to do is just give him access. When he runs a query against my data, he will get charged. It'll go against whatever computing resources he uses to run that query. So I like that. It simplifies that cost model, and really it works really well. So I just thought if you're doing data exchanges or data sharing, you might want to check that out, because I'm sure other vendors may offer things in the future, but I haven't seen it yet. They're one of the first ones I've seen do this, and I think it's brilliant. Cloud or on-premise. So I wanted to talk about this a little bit. When you can talk about cloud, it's a different kind of cost structure. You're paying for renting hardware monthly, hardware and software, versus on-premise, where you have an upfront investment. And with hardware, you typically have to refresh your hardware every 5 years. So there's pros and cons to both. I use both. I still, enjoy very much, investing in hardware, and I'm a big proponent of on-premise. In reality, the cloud is somebody else's computer, so the things that they worry about in the cloud are the same things that you would have to worry about on-premise. Their networking, the infrastructure, the security, the routers, the bandwidth, your switches, storage, your servers, carving out those servers, and like whether customers are going to share computing resources or whether they're going to have their own dedicated resources, storage, all of that stuff. So it's just, they've just made it easier in that you don't have to do the hardware maintenance. You can just request that service online. But I will say that moving from on-premise to the cloud, be careful, because I find that nowadays a lot of students that aren't getting the benefit of the hands-on infrastructure and engineering expertise, when they go to the cloud, they may not, there's that skill gap where they don't understand the repercussions. So if you are carving out services in the cloud and enabling data access, you still have to worry about, like, whether when you carve up a new computing resource. Does it have enough, what are the specs of that resource? Does it have enough CPU power, RAM power, storage? Is there any network? Are there any IO bottlenecks? Anything like that? Those are things in the past when we did on-premise, or we used to have to, we would monitor those, the resource constraints and scale up as needed. Well, that hasn't changed in the cloud. So if you find that you've gone and you're doing something in the cloud, you have a computing instance and it's not performing the way that it should, some of the things you need to ask are, what are the bottlenecks? The same questions that you would ask on premise are still there in the cloud. They're just packaged differently. Some of the popular vendors, Microsoft, Azure Service, sometimes the terminology is changing a little bit too. So, and Microsoft, they've labeled everything as Azure, but in terms of computing and directory and databases, it still translates well from on-premise to the cloud. They're computing resources, they call them virtual machines. With web services, sometimes with Amazon Web Services, they're one of the other vendors that we use quite a bit. EC2 is pretty much what they call your virtual machines. So there's a little bit of changes in terminology. And then you have your Google Cloud Services. I'm not going to go into each individually. Just know that whichever one you use, it's the same concept. What are the computing resources you need? What are your databases? What type of storage do you need? Are you going to use big data storage, or do you need file storage? Those are just questions to ask. They all have they all do a good job of documenting this stuff. It'll take a little bit of research to figure out how that translates into what you have on premise already, if you're doing a migration effort. IBM, they're one of the newer kids to the cloud arena, but they've made a lot of headway. And I find that, I actually like the way that they have if you go and spin up a virtual server, it looks very much, it has that very much traditional feel when I used to use VMware or Hyper-V, where it's kind of easier to translate the on-premise hardware of here's a server and the specifications and let me spin it up in the cloud, compared to some of the other vendors where you're actually looking at, okay, well, what's the instance and what does that mean? And I have to do separately look up those instances, versus where IBM tends to spell it out a little bit more. And the other thing that IBM's getting into, and Microsoft also has this, is mainframe in the cloud. So, which is kind of a brilliant thing and might help some of your modernization efforts. But Azure also has a mainframe capability in the cloud too. So that's relatively new. I haven't played around with that a lot, but maybe that will help you create a sandbox. If you have a mainframe footprint and you don't want to interfere with your development efforts, you can perhaps spin up an instance in the cloud and do some staged proof of concepts. Advanced data science platforms, and I'm going to have to kind of rush this a bit because I'm running out of time. But one of the things, so when you've done the research and you've figured out where you want to go with your infrastructure, your hardware, what type of data warehouse you're going to have, the other piece that you need to figure out is what tools are you going to provide to your data scientist and your analyst. There's some wonderful data science platforms out there. I've used all of the ones I've listed here. So a lot of these tools require that your staff are skilled in Python, Java, or R, but not just it's more, they need to know more than just how to program this stuff. They also need to know what the algorithms are. They need to know what a regression model is. They need to know what a neural network model is. They need to understand how to interpret the outputs. So you really have to understand that you have to make sure you have the right mix of staff. You may have to have a data engineer, a data scientist, and or even might even have like a data engineer, a mathematician or statistician, and a programmer, and pair them up so that they can each do the pieces that they need. You might have the programmer help work with the statistician to use these workspaces to build these algorithms in Python, but then have the statistician know how to interpret the outputs. The nice thing about these workspaces, especially the Databricks and the Azure, is that you can scale out and add more computing power as you need to handle some of the workloads. Google Colab I really like a lot because they've enabled a lot of GPU instances, and they're cost effective, and there's even some free versions that you can use. And they have lots of sample code. It's really, I have my students work in Colab quite a bit. It's a really nice platform to learn on, and I see them, I wish I had time to show you more, but just check them out. There's the link. So the last thing I'll mention is there's a lot of no-code and AutoML data science tools, and I'm a big fan of those as well. So if we go back to the old slide, yes, you can have your team write things in Python and stuff, and that's fine. But when you get to the point that if you only have a couple of skilled data scientists and you have a lot of work for them to do, why not explore some of the AutoML tools to automate some of their work and help them to be more efficient? So like Data Robot is this wonderful tool that you can feed it a set of data and it will give you 20 different algorithms and compare it, and it's not transparent. So I love that too. So you can actually see inside like why it selected the models, what parameters it used, what the outputs were, and then you can use it'll identify the top performing models, and you can agree or disagree. You might want to go back and tweak your data. But then when you pick the best performing model, you can then just generate you can have it generate some Python or Java code and operationalize it. So that's just wonderful. It's a real time saver. I have no problem with taking a data set, pushing a button, and having it do all of the programming for me. And then I can just focus on the output. There's other tools that can do similar things. H2O.A is another one. SAS, they have a lot of visual and specialty AI tools. Like TextMiner is one of them. There was a competition that Kaggle had where you were trying to predict the level of gene cell mutation based on and you were trying based on a bunch of submitted text evidence, and they had a model, pretty much you would look at these volumes of medical literature and stuff where a scientist had gone in and said, this is indicative, this is the background that supports that the cancer cell mutation that we've labeled for this cell. And so one weekend I was like, well, I don't have time to work on this, but let me just use TextMiner and see what it does. And I ran it through on trained the model, and I looked at the test model, and I turned it in as is. I didn't do any tweaking, and I finished in like the top 20 out of 3,000 entrants. So SAS is still a player in the market. So if you're using them, they're actually one of the mature products that have a lot of really good, especially their SAS foundational tools. They have a really lot of really great algorithms that have evolved, and especially their their optimization models and stuff. So they're still a contender. And then AWS and Azure, they both have a lot of decent AI tools, and that may help your data scientist offload some of the model building part and being able to compare different models. So those are some of the things in your tool set. So in closing, just remember, are you ready for AI? The essential ingredient to effective implementation of AI is a solid data infrastructure. Your data must be available. You must be able to access it. It must be in a format that you can analyze it. You should assess your existing infrastructure, target your data systems to your business use case, evaluate your current environment, and then have the right analytic tools and skill set. All of this is critical. So many things to consider to make sure you're ready and that you can make effective use of AI. So thank you, and now I'll entertain any questions that you